All right, so for this video, we're actually going to go back to the same packet that we were on in class the other evening that dealt with chemistry. We got through a lot of the main topics in looking at the basic structure of the atom and how it behaves. And one of the biggest things with that is just understanding the basics of positive and negative charges and how they interact with each other. And while we apply that to chemistry, and it's a very big part of chemistry, it is also the very foundation of how the human body works. It's how we get things like nerve impulses to fire, it's how we get muscle contractions to happen, is by making sure that we get those positive charges in a certain location, a negative charge in a different location, and we only allow them to interact with each other when we want something to take place in the body. And so, as I mentioned the other day when we were in class, even though atoms and protons and neutrons and electrons and all of that seems like a very chemistry thing, it is also going to be the explanation for how we function and how we are able to survive. So we got through most of the atom material. We talked about the design, we talked about the different types of bonds and why those bonds happen. We talked about ions and isotopes, but we also need to look at a couple topics that we didn't have time to cover. And so I do want to go back and pick that up. Um, and actually, where I want to go is going to be to the pH information. So on page 6, there is a couple slides that talk about pH levels, and that's where I'm going to pick up for this particular conversation. All right, so looking at pH, you'll notice right away that the first letter is lowercase, second letter is uppercase, and that's intentionally done. The other evening I passed out periodic tables to you guys in class, and you'll notice that the letter designations for the different elements that we have on the periodic table, the first letter is always capital, and some of them only have one letter. But for those that have two letters, first letter is always capital, second letter is always lowercase. In the pH scale, they wanted to flip that so it was identifiable as being applying to the pH scale and not being one of the elements on the periodic table. So that is why you see that lowercase first. What it actually stands for, and there are different interpretations of this, but a lot of people will explain it as being the power of hydrogen. And when we look at the pH scale, if you're not overly familiar with that, you have your basic water molecule, which is H2O, 2 hydrogen atoms to 1 oxygen atom. And when that's a water molecule, they all stick together, but there are certain situations where that water molecule will break apart and it's no longer H2O. One of the hydrogens will go off by itself and the other hydrogen and the oxygen will go off by themselves. And so the water molecule breaks apart and goes their separate ways. When that happens, that one hydrogen that goes off by itself is called a hydrogen ion, and the oxygen and the hydrogen that go their way are called a hydroxide ion. And those are the very particles that are going to make up our pH scale. The pH scale is a measuring tool that we use to see how many of those hydrogens, those H pluses, we have in a particular solution. So when you look at the top of page 6, it talks about the concentration of hydrogen ions in a solution. Where those hydrogen ions are going to come from is from a water molecule that breaks apart, goes from being that H2O into a hydrogen and then a hydrogen and an oxygen. For the overall pH scale, it is going to range from 0 to 14. So the lowest number you can have on a pH ranking is 0. The highest you can have is 14. Neutral is considered 7 because it's right in the middle. And when we look at the pH scale, more people are used to hearing about acids and bases. And that's essentially what the pH scale is looking at. Anything that is below a 7 on the pH scale is going to be considered an acid, and anything higher than a 7 on the pH scale is going to be considered a base. Now, the unique thing about the pH scale is usually on a measurement tool, you start at 0 and you go away from there and you get higher. On the pH scale, the starting point where you have no acidic or no basic properties is at 7. And as you move further away from 7, the acid will become stronger or the base will become stronger. So if you're at 7 and you go to 8, up to 9, up to 12, up towards 14, as you get closer to 14, that base is intensifying in strength and becoming stronger. On the other side, if you are at 7 and you go from 6 to 5 to 4, get closer to 0, the acid is becoming stronger. So 7, no acidic properties, no basic properties, but as you move away towards the ends of the pH scale, whether you're moving up to 14 or you're moving back down to 0, the intensity of that acid or that base is going to become stronger. So like I said, it's a little bit different than your typical measuring tool and how it works. When we look at the pH for the human body, the pH level for us is going to be 7.4. Now, with that pH level being at 7.4, it is also one of our set point values that has the smallest degree of change before there's really adverse problems. If you think about body temperature should be 98.6 degrees, but it can swing up to 102. It can drop a few degrees below 98.6, and you really don't have any serious issues. Once you start to hit around 105, 106, then there's serious concern for that. But when you look at the pH scale, 7.4 is where we should be. At 7.45, that's when we start to have issues within the body, or in the other direction at 7.35. So really, when you look at pH and maintaining pH level in the human body, you have a very small range in which you can fluctuate away from that 7.4 before it actually starts having some adverse effects in how our internal structures, our internal organs are able to work and perform their jobs. All right, if you flip over to page, sorry, my page numbers are out of order. If you flip over to page 7, page 7 gives you a visual of the pH scale, and you'll see the pH scale kind of drawn in different ways. Sometimes you'll see it as a rectangle, actually going vertically. This one is arranged horizontally. It shows you 7 right in the middle, and then ranging up to 14 if you're on the basic side, and ranging down to 0 if you are on the acidic side. One thing that I would like you to do is, if you look at the numbers 8 and 9 on the pH scale, and if you are on the pH scale and you move from a pH level of 8 to a pH level of 9, for a lot of people that don't have a lot of background with the pH scale, that doesn't seem like a big deal. Moving one spot is not that big. But in actuality, if you go from 8 to 9 on the pH scale, that base has increased its strength 10 times. So between those numbers 8 and 9, I would just like you to write a 10x to indicate and remind yourself that that is increasing by a power of 10 just in moving that one spot. So if you would go from a pH level of 8 to a pH of 10, now you've increased 100 times, because it's 10 times from 8 to 9, 10 times from 9 to 10. So 10 times 10 is going to get you to 100 times the strength. So the intensity level is able to jump very quickly, much more than what it looks when you're just moving one spot on the pH scale. Now that holds true on the acidic side as well. If you go from 5 to 4, it's increasing 10 times. If you would move from a 5 and jump to a 3, it's now increased by a power of 100. So like I said, a little deceiving, but you have big change or big swing in the strength of your acid or your base, even moving a small distance on that pH scale. A lot of times when you see pH scales, I know this one's not in color, acidic sides are typically drawn in red, basic sides are typically drawn in blue. And I think sometimes people get kind of a misunderstanding of that as well. We know red is kind of the danger color, and blue is typically considered to be more of a neutral or safe color, and that's not the case. having a strong base can be just as serious as having a strong acid. We think of acids burning and things like that, and a base can do the exact same thing when you start to get into those higher numbers. So they are both capable of doing extreme damage, especially when they get into those higher values. If you look at the bottom of page 7, it just talks a little bit more about exactly what an acid and a base is. And going back to the original explanation that I gave you, when we think of acids and bases, we know that they are able to do damage within the body. They're able to do damage to soft bases and when they interact with certain things. And it's interesting if you really stop and think about it that where these two acids and bases originate from is from a water molecule. And water is something that we use every day. We bathe in it, we drink it. We don't think twice about it if it comes in contact with our skin. But in the right conditions, if that water molecule has to break apart into smaller pieces, it actually becomes the very thing that can do damage to our body. Now, when you have your hydrogen ions, which make up your acids, and you have your hydroxides, those OHs, which make up your base, they also are looking for an opportunity to return back to their water state. So if they can find a way to do that, they will take advantage of it. So you have that H2O water molecule that broke apart. Hydrogen went its way, the oxygen and hydrogen went their way. But if that oxygen and hydrogen find a free hydrogen, they will go back to being a water molecule. They will return back to H2O. And you guys have probably felt this and experienced it, but just not realized exactly what's happening. If you think about cutting an onion, a lot of people have a very adverse reaction to cutting onions, and that's because there's an acid in it, and that acid gets into your nasal passages, that acid gets into your eyes. And the reason that it triggers a response is because those H pluses are looking for a way to return back to water. They're actually stealing the water out of your tissues. And as they pull that water out of your tissues, you feel that stinging and that burning as those tissues are losing that water and kind of reacting to that. And so, like I said, if you've ever smelled ammonia or anything that has a very strong acid or base content to it, you'll notice that stinging sensation, and that's exactly what's happening. They're trying to return back to their water state. They're pulling that water out of your body to do that, and you feel your tissues tightening as they are losing that water content. Go ahead and flip over to the last page, which talks about the organic molecules that we have in our bodies. And actually, I want to change that a little bit. I want to talk about the macromolecules. So macromolecules, macro indicates large, molecules telling you that you have more than one element that are combining together to form a particular structure. So we have 4 major macromolecules in the human body. And one of them is carbohydrates. So that's the one that's listed on that top slide. But we do have some others that we need to talk about as well. And those are listed at the bottom of the page. So you have lipids, you have proteins, and then you have the nucleic acids. So carbohydrates are going to be our main energy source. When you guys put calories into your body, when you guys eat foods, the very first thing that you're going to tap into are those calories that come through in the form of carbohydrates. Those are the first ones that you burn through and that you use up. So carbs are very important because that is your first source of energy. There's a lot of diets out there that will tell you to cut carbs, and the driving force behind those particular diets is that if you don't have the carbs in your diet, you immediately go to burning the fats in your body. And so it's a little bit of a way to kind of change how your body functions. Don't give it the carbs, it's going to have to burn off the fat. Now, when we look at fat, fat has a lot of different functions in the body. It is going to work as a way to maintain our body temperature. So it's kind of like an internal blanket that we have. It's also going to offer protection to our bodies so that as we bump into things, we have a little bit of cushion so that we're not damaging a lot of internal structures, we're not bruising very easily and things of that nature. That will also serve as a way to fill extra space. There's a lot of places in between bones where organs meet and come together, and it's not a perfect fit. So we have that fat tissue, which is going to push into those areas and kind of help make all of those pieces and those structures fit together in a little bit better way. And then it's also going to serve as a secondary energy supply. So as I mentioned already, we're going to burn through those carbs first. When you burn through those carbs and you still need calories on the day, then you go into your fat calories and you'll start burning those off. And so we rely on it as a backup essentially for our carb calories. Anything that you don't burn off through your daily activities, if you have more calorie intake than you burn off, then what's going to happen is those extra calories will then get stored as fat. So you have those secondary reserves. We don't just pass those calories through because some of our body functions still work on kind of caveman mentality. There was a time period where you didn't have grocery stores to go to, you didn't have refrigerators in your home where you could stockpile food and things like that. It was a hunting and gathering type situation, and you had to go out and you had to fight for your food. And because of that, food was not always readily available. There could be long time periods between meals and things of that nature. And so the body designed a way that if you ever did have extra calories, you would hang on to those so that in those lean times, you could tap into those reserves and still survive. And so we never get rid of calories. And that is our body's way of trying to be efficient, just making sure that if we ever do run out, that we can fall back on those reserves that we have. The other macromolecule that we have are the proteins. Proteins, when we look at those first three actually that I've talked about, the carbs, the lipids, and the proteins, those are the only three places that we get calories. So when we look at food labels and things like that, there's a bunch of information on there. But the calorie content is only going to come from those carbs, those lipids, and those proteins. Carbs are going to give you about 4 calories for every 1 gram that you eat. Proteins are going to give you 4 calories for every 1 gram, excuse me. And then lipids are going to give you 9 calories for every 1 gram. And that's a little bit of rounding in there, but 4 for the carbs, 4 calories per gram for proteins, and 9 calories per gram on the fats. Now, the thing of it is, carbs are your first source of energy, fats are your second source of energy. Proteins, even though they offer the body calories, we never ever want to have to use those proteins as an energy source. And the reason for that is proteins are used in so many places in the body as a building block, as a building material. We use the protein to build our muscle. It's in our skin, it's in our hair, our nails, our cell membranes, our DNA, our organelles. Protein is pretty much everywhere. We use it in some way, shape, or form to build almost every part of our body. So we don't want to have to devote those proteins to supplying our energy needs. We try to keep that to the carbs and the fats. If you are having to tap into your proteins for energy needs, something is wrong. You are being starved, whether that is self-inflicted or just lack of food, but it's not a good situation when you're having to use those proteins to supply or fuel your body. We try to keep that for building only. And then we get to the last macromolecule, which is going to be nucleic acids. Nucleic acids are going to build our genetic material. So they are going to be responsible for the structure of your DNA. DNA is found in pretty much every cell that we have in our body, and every time a cell divides and becomes 2 cells, a copy of that DNA is made and goes into each one of the new cells. So that, like I said, majority, there are some exceptions, majority of your cells are going to hold all of your DNA. DNA is essentially a blueprint for how to make you. It is all the instructions for your eye color, hair color, how tall you're going to be, just every feature that makes you up. All of that information is held within that DNA, and it's the job of those nucleic acids to make that up. Now, I know on schedule-wise, We were not going to finish that up, but it was information that we need to talk about, especially with the pH, because pH is going to show up quite a bit as we move through different things. When we get into the stomach, when we get into the kidneys and things like that, pH levels and understanding how that works. It's going to be something that we talk about multiple times. So we'll get everything back on track as far as the schedule goes. Don't worry about that. But it was very important that we picked up that part of the information. So Tuesday, your assignment for this week will be posted. Shoot me an email if you have any questions, and I will see you guys later.